Hello, everyone. Welcome to the Reinforcement Learning Reading Club. In this session, we will be reading the paper about multi-agentic reinforcement learning from ICML 2019, and the presenter is Wenshuai Zhao, a PhD student in Aalto Robot Learning Lab. So, Wenshuai, you can begin.
Hi, yes, okay. Hello, everyone. I'm very happy to present this paper here. The title is called Social Influence as Intrinsic Motivation for Multi-Agent Deep Reinforcement Learning. And this paper receives the outstanding paper honorable mention in ICML 2019. The authors is Natasha, Jaques, and the other guys. Okay, first let's use one sentence to introduce this paper. I think we can use like this paper use social influence as an additional reward to encourage agents to learn to cooperate, not to be selfish. So what is social influence? It's just a measurement to measure how much one can influence other agents. Okay, so in this presentation, we will introduce sequentially from problem formulation and benchmarks and typical multi-agent reinforcement algorithms, and especially introduce the social influence reward proposed in this paper. And then we introduce 3 experiments and also connect this paper to other related work. Okay, first let's talk about the problem formulation. In this paper, we focus on this partially observable Markov games. In this formulation, we have n as the number of agents, and s is the global state of the whole game. And each agent has its own partial observation, is indicated as OI, and each agent also has its own action spaces. And P is the transition probability, and especially in Markov games, each agent has its own reward function. So the aim of agents are trying to maximize their own reward function. So it's like that. That's here. The second, we will learn about social dilemma. Social dilemma is very common in game theory. For example, this famous prisoner's dilemma. C here means the cooperator. D means the defector. So who doesn't cooperate, but defect, but cheat others. So in this prisoner's dilemma, we can find if both of them, the 2 guys, they cooperate, so they can get both 3 the rewards. But if they both defect, so they can only get 1 reward. So this is the worst case. But if one cooperates, another one defect, so the defector one will get a higher reward than the cooperative one. So this is the dilemma. And formally, it can be expressed using these 4 inequality equations. So it's like from here, R is the reward when they cooperate, P is when they defect both, and S is the one when only one cooperator and another one defector. So S is the reward of the defector of the cooperator, and T is the reward of the cooperator, the defector. So importantly, we should notice that the collective rewards to R here should be greater than the total rewards achieved by the situation that 1 cooperator and 1 defector. So in this dilemma, we encourage people to cooperate, not learn to defect, right? So in this paper, we study sequential social dilemma. It's not only the one action social dilemma. So we call this sequential social dilemma, SSD. So we can simply think it as Markov games whose reward functions satisfy this SD inequalities. So just for simplicity. Okay, so we can after learning about the formulation of the problem, so we can see two examples. Actually, they are our benchmarks in this paper. First is called clean up. So we can see this this picture. It's a little doomy, but let's see what's the meaning here. The green box here, many green box. They are apples. They are apples. Okay, so this part blue blue box. No, a very long blue. They are river. So and this stuff are the waste. So what's the logic here is we should keep the river. The agency should keep the river clean over one threshold in order to farm more apples. So the agents they want to collect more apples, but if they don't clean the river, so after the apples are eaten up, so no new apples will be grown up. So they have to spend some time, spend some more effort to clean up the waste. So the dilemma in this benchmark is that an individual must pay a personal cost in order to provide a resource that is shared by all. So because one agent, if he doesn't collect the apple, he goes to clean the river. He cannot get additional payoff, but there are some agents they have to do that because if they all collect the apples, no one goes to clean the river, so the apples will quickly be zero. So that's not good for each for each agent. The second benchmark is similar with the first one. It's called harvest. It's called harvest. So in this case, the green boxes are also apples. So the colorful boxes are agents. So they want to collect the apple, but the apple regrowth rate is dependent on the near apples. So for example, this part there are many apples. So if one agent eats one apple, so another apple will grow very fast. But if all the apples are for example this part, no apples, so no new apple will grow. So it means the more nearby apples, the higher local regrowth rate of new apples. And for these two benchmarks, the observation of agents are 15 by 15 image. So in this benchmark, the agents should learn to constrain themselves. So they cannot only eat apples all the time. They should, especially when more agents are in the same local region, they have to constrain themselves and wait and don't not always eating the apples. So this is called a commons dilemma. And in the last benchmark, it's called the public goods dilemma. So they are terminologies from game theory maybe. Okay, these two figures are called sharing diagram. So these two figures especially indicate in which situation they can get higher collective rewards. For example, let's say this one is for the cleanup benchmark. This red line indicates the reward of one defector, and the blue line means the reward of one cooperator. So, for example, here it means if this guy is a cooperator, and for the other agents only one is a cooperator, so its reward is 150. But if the other agents there are more cooperators in cooperators, so we can see this guy's reward will increase, and similarly as a defector, its reward also increase if there are more cooperators. This is similar in the harvest benchmark. Okay, so I have introduced the benchmarks. If there's any questions, so anybody can stop me. Okay, let's introduce the algorithm. So normally multi-agent reinforcement learning algorithm can be split into two ways. One is called centralized training and decentralized execution. It's called CTDE. So what's the meaning? It means we set one policy for each agent, or maybe not every agent, but they can also share a policy between some agents. But the important is for the value function, it should be centralized. So because we want to guide the agents well or better, so we want to our value function is more robust, is more accurate. So so our value function should based on the global state, so we can borrow some states from other agents, so we know the whole global state. Or if we are using some Q learning like algorithms, so we can learn our Q function based on actions, not only including our own actions, but also including other agents' actions. So this is called centralized training, because we are using some information from other agents. But independent learning means we don't borrow any information from other agents. We only use each agent's own information, its own observation, and its own action to learn its policy. And the parameter sharing means if we use the same policy for some agents, or if every agent has its own special policy. Yeah, so that's the meaning of parameter sharing. And in this paper, they use both architectures here, and but finally they want to develop some independent, purely independent learning method, because they think centralized training is not so realistic in the realistic applications. So they want to develop independent learning methods. This is the basic architecture network used in this paper. So because the two benchmarks are both partially observable, so they introduce some RNN-based module in their network. So we can say it's very classical. The value function and the policy share part of the layers, and the training method they use is the SRC. Now let's talk about the social influence reward. This is the main contribution in this paper. So it's very straightforward. Usually, the reward of each agent is only produced by the environment ET K here. K means the index of the agent. T is the time step. But in this paper, we introduce another intrinsic reward. It's called CTK here. So it's the social influence reward. And we use two hyperparameter alpha and beta to combine them for every agent. Okay, so let's see what is C here. C actually it's computed based on the so-called counterfactual actions. Okay, let's first think about we want to compute how much we can influence another agent's action. So we assume another agent, for example, is G, the agent G, but we are agent K. So we want to know how much we can influence the agent G. So we know agent G's action is based on agent K's action and its own state. So we know this their policy is conditional on our action. So the counterfactual action is we ask how would G's action will change if we act differently. For example, we choose this action, but we can also choose imagine we are choosing other agents, other actions like this tidal AT K here. So we can also compute. We can also use this probability to indicate how much other agents action will change. So formally the reward is computed by compare the actual probability of action ATG and the difference between this probability and other accumulated probability based on other actions ATK with this height. Yes, so if we accumulate this summation, so we can get this marginal probability. It means we compute the some distance. Here is the KL divergence between the probabilities of agent K's action ATJ when it consider our action ATK and another case when they don't consider our action. So formally we can think this equation will indicate how much we can influence the agent J, right? So it indicates how much agent K influence the agent J, and we accumulate over all other agents, especially except ourselves. So we accumulate this summation here.
Excuse me, but we are still not sure if this is a positive influence or a negative influence, right?
Sorry?
We are not still sure if this is a positive or negative influence, like if it's collaborating with the other agents or competing with them.
Yeah, I think we don't know the positive is positive or negative.
Yeah, okay.
But yeah. Okay. No. But I think chiral divergence is also is always positive, right?
Yeah, but I mean, but I mean, how? So it's just computing the distance between these two distributions. It doesn't say anything about the reward, right?
Yes. Yes. Here he's using chiral divergence, but it also these people also states that they can replace the chiral divergence with other distance functions.
Yeah.
Maybe in that case, in other cases, we should consider is positive or negative.
Mm-hmm.
Yeah, but here they use chiral divergence. So I think the sign is consistent of the reward.
Yeah. Okay.
Okay. So we know our main idea of this paper is using this social influence reward to be additional reward. Okay, let's see our experiment. The first one is the basic social influence. It's called because why it's called basic, because we are using because in this reward function we are directly using other agents policy. So we know the probability of some more actions of other agents. So we directly know. So we use that to compute the reward for agent K. So it's assuming we know much more information than we should have. So it is called basic. But the results is showing that this influence reward will help get a better performance in both two benchmarks. So we can see the red line is higher. But we should note that in this case it's called centralized training because we are using more information. And in this experiment, we can observe action-based communication. So because we use our action to influence the other agents' action, so it's like the bee waggle dance. So we use our action to communicate with each other to cooperate. So let's see this video. This is a very short video. Okay, it's too fast, but let's slow down it. I don't know if you are confused now. Here we can see here. Can you see my mouse?
Yeah, but can you make it bigger? Yeah. So yeah.
Yes. Here it's okay. Yes. So let's focus on this figure. Actually, in this experiment, they are trying to show that if we know this, we call this purple box, purple agent is the influencer. So it tries to influence other agents by its own action. So how can it influence others? We see that when there are many apples green box here, so this purple box will go randomly, but no, it will go randomly. But if there's no apples, so it will stop at the left border. So it's not like other agents still continue work randomly. And when there are some apples generated, so this agent will go right. It will go to the right part. Go to the, yeah. So it means other agents can observe this proper agent's behavior. When it stops here, they know, oh, okay, there's no apple, so they should go to clean the river. And if this purple agent they go this part, they go to the down, go to the bottom of the figure, the other agents should know, oh, okay, there are some new apples, so they can go to eat the apples. So it's very interesting. They think in this experiment, the agents learn to communicate or learn to cooperate by their own actions, because they think the purple agent's action influence other agents. Okay, let's continue to the second experiment, because in last experiment we think we observe some more action-based communication. We think they use their own action to communicate with other agents. So that in the second experiment they try to use some more explicit communication channel in agents. So in this experiment they are using this they're using this new architecture. We introduce the messenger channel to the RSTimo part, and we learn two different stuff. One is for the normal policy and the normal value function, and another one is called message-based value function and policy. So the reward for this normal stuff is still using the true reward. It's from the environment. It's EK. But for this part, they are using rewards including social influence. Yes. So in this case, our influence reward can be computed by this function, by this equation, and we replace the action of other agent action. We replace the action with this messenger MT -1K. Yeah. So in this case, we should note that we can model freely the influence reward between any agents, because later we will talk about that in the first experiment, we cannot freely compute the social influence reward for any pairs of agents, because we should consider the sequence of the action. Because we use this action to be conditioned on, so we should avoid some circular dependence. We will talk about it later. But in this communication case, they can freely model the influence reward between any agents. And for the third experiment, because in the last two experiments, we are still using additional information from other agents, right? We know there are action probability, or we use some more explicit computation. But in the third one, we finally release this assumption. We want to get one purely independent training. So we don't know the action probability of other agents, but only observe the actions. We can observe the actions, but we don't know their policy explicitly. So here we use this architecture. In this case, we observe. We have our own observation, and we also observe other agent. We also have our action, and we can predict some other agents next action. So I think this is not so clear. So actually it means this one. So we still model, we still compute agent J's action based on agent K's action, right? It's here. So we can in this architecture we are still computing the social influence reward of agent K. So we in this model we compute the probability of agent J, and for other agents, I think we can repeat this module to other agents. So this is for J, it's for J+1. So we can repeat this part to more. And some details is that in this part they only compute the social reward function of reward on agents in case view. So if some agents are not observed in this observation range, so we don't compute the influence reward. So this should be noted here. I think this model is the perfect one in this paper because this is the main difference with some existing paper. They don't need additional information from other agents. And to train this part, it's very straightforward because we predict other agents' action, and we can observe other agents' action. So we have some more supervision signal, so we can back propagate the gradient. So it's okay. For this experiments, there are some details we should know. At first, we have some special hyperparameters in addition to regular ones in reinforcement learning. For example, the first is the number of influencers. We should know in the first basic experiment, we should constrain the number of influencers because we cannot enter into a circle. And also we have some more alpha and beta as hyperparameters. We should make a schedule in our training to how to set how change them. And also for the second experiment, for the implicit communication protocol experiment, they also propose some measurements to analyze their performance. But I won't introduce detailedly here. So we know we can measure the learned communication protocols. Yeah, we can analyze the performance specifically. And the second detail we should know is we can use a causal influence graph to indicate our logic in our experiments. So for example, for the basic experiment, for the first experiment, the graph is like this. It's like this because for example, we have a state of a global state TST, and it can be split into state of agent K and agent J, and they based on the state they compute some hidden state of K and J, and they choose their action based on this hidden state agent K agent action of agent K. So we compute. So in this case, we compute the influence reward of agent K because the agent J's action is based on agent K. So we should note that for this case, to avoid circular independence in the graph, agent K must choose its action before J. And therefore, K can influence J, but J cannot influence K. So it's not very flexible to compute to compute the influence reward between any agents, between any agents. So this is the right one is for the model-based experiment. In this case, it's a little complicated because we learn some model. So the green shaded elements are the stuff we try to learn in our model. So even though we know our own action and the other agents' action, we observe other agents' action. So we try to predict agent J's next action. So this stuff are not given. So this stuff are learned in our model. Yeah. Okay, so let's talk about some related work. Social influence actually has been used in other papers, but they are used in different ways. For example, first we know we can handcraft some reward for cooperative behavior. If we can know, we can define clearly what is a cooperative behavior. So we want to encourage it. So we can give some more reward. So it's very straightforward. And for some other automatic generated reward, we can use different ways. For example, we can observe other agents' rewards. We can use our action to influence other agents' rewards. It's also has been used in some papers. It assumes we can observe other agents' rewards. So we can compute, for example, how much our action can increase or decrease other agents' rewards. So we can use this influence as an additional reward, as an intrinsic reward. And in this paper, actually, we are using this case. We are trying to measure how much our action can influence other agents' actions. And also we can compute how much our action can influence our own future state. But okay, this concept is used in single agent reward. It's called empowerment. So we compute the mutual information, like for example, the mutual information between our action and our own future state. So we can condition our action based on the rewards and actions and state. So it's very interesting. And in this paper, they also prove that the social influence reward they propose actually is equal to the mutual information between agents' action in expectation. In this equation 5, this is the definition of mutual information between two agents' actions. So they are conditional on the they can be seen as the state of all the information we need to compute the action. So this is the definition of mutual information, and we can reform it as this one. So we know this term, the characteristics, is actually what we use in this paper is social influence, and we can write it like the expectation of our social influence. So it's equal. Yeah. So I think these are all the content in this paper.
So, thank you very much, Wenshuai. So, is there any questions or comments? Yeah, okay, Tuan, thanks. Yeah, it was it's still a bit interesting to me that like when computing the social influence, it's not taking into account the reward of the other agents or something like that. So yeah, but it was interesting to see that it's still improving the results. Maybe there is something with the, I don't know, there is something in the configuration of the environment that encourages like positive influence or collaboration between agents. Not sure. But anyway, yeah, okay. So thank you, Wenshuai, for the presentation, and thanks all who attended. So hopefully we'll see you in the next session. Yeah.
Yeah. Thank you, guys.
Thank you. Bye.
Bye.